Wien's law. We have seen already the idea that hot objects produce light that has a short wavelength, and cool objects produce light with a long wavelength. And so, conceptually, we can look at something that's blue and know that's hot, or look at something that's red and know that that's cool. But what Wien's law allows us to do is to actually calculate the temperature rather than this very generic hot versus cool comparison. And our equation for Wien's law is that T, which is our temperature, is equal to this constant, 0.0029, divided by what we're calling lambda max. And what lambda max refers to is basically the wavelength that is brightest. Because when objects give off light, they give off light at all wavelengths, or pretty much all wavelengths. So here we're looking at what wavelength is that object the brightest, and typically that's going to relate to the color. So when our sun, for example, looks mostly yellow, which we see here, that is because the wavelength where our sun is brightest is at the yellow part of the spectrum. And in this illustration, here we have something that's brightest in the blue and something that's brightest in the red. So here's our brightness scale. We're looking to see where is it the brightest, and then reading off the corresponding wavelength. For our sun, the actual wavelength is 5 times 10 to the negative 7th meters. The actual scale is different. This was measured in angstroms, which is a unit popular in astronomy, but for our equation we want to use meters. So here we see our sun spectrum, and the way they have it drawn, it's at about 6,000 angstroms. What I've got would be equivalent to 5,000 angstroms, but it's right around in that ballpark. So if we plug that into our equation, we're going to use that 5 times 10 to the negative 7th meters as our lambda max, and we just plug that into the equation. We always use the 0.0029. That constant doesn't change. And now we're going to divide it by 5 times 10 to the negative 7th. And notice we've got parentheses here. Now if you use the E button, this would be 5 EE negative 7. You would not have to use the parentheses. But if you actually plug it into your calculator as 5 times 10 caret negative 7, that you need the parentheses for, so your calculator treats that all as one number. And the answer you should get is 5,800 Kelvin. Kelvins, that's a temperature unit that we don't encounter on a daily basis. When objects have a temperature, they jiggle. And basically, the hotter something is, the faster it jiggles. And we're talking about on the atomic scale, so we're looking at individual atoms going on here. And so as it gets cooler, it's going to get slower. And the point where it stops moving, that temperature, is called absolute zero. So that's the temperature where motion stops. So even just the individual atoms have no motion at all. Now, the way our temperature scales are set up, in Celsius, absolute zero is negative 273 degrees Celsius. On the Fahrenheit scale, that is negative 460 degrees Fahrenheit. Notice that neither of those numbers is zero. So the Kelvin scale was set up so that absolute zero is 0 degrees Kelvin. And for whatever reason, we don't use the little degree symbol for Kelvin. We just use a K. So 0 Kelvin is absolute zero. The size of a change in temperature, a change of 1 degree Kelvin, delta, the little triangle means change, is equal to 1 degree Celsius change. So 5800 Kelvin is 5800 degrees Celsius above absolute zero. Is the way to think of that. Now, when you're talking about temperatures this big, a few hundred degrees isn't going to make much difference. So it's going to be hot. And if you want a very rough conversion for the kinds of temperatures we use in astronomy to Fahrenheit, take it and just about double it. It's not going to be accurate, but it'll get you in more or less the ballpark. So around 11,000 degrees Fahrenheit. Now this is the surface of our sun. It's actually much, much hotter in the interior. But Wien's law, by using the wavelength of the dominant light, in this case yellow, tells us how hot the surface of the sun is, or any other star.